Welcome back. Working through a few more kinematics examples. Let's see what we can get done here. So, rising upward at 10 meters per second in a hot air balloon, you drop your camera at height of 14 meters. Determine maximum height. So, if you're in a hot air balloon and it's rising 10 meters per second, you are also rising at 10 meters per second, and so is the thing in your hand. So when you let go of it, it doesn't start falling right away. At first, it is rising at 10 meters per second, and we would call that our initial velocity. But as soon as it's out of your hands and free to fall, gravity gets a hold of it and it starts accelerating downward at the usual amount for Earth, 9.81 meters per second squared. Everything on Earth that isn't powered by engines or wings or held up by something falls at that rate. That's Earth's gravitational acceleration. So this object will start at 10 and then it'll go 987654321 That's when it'll reach maximum height, and then it'll start going -1, -2, -3, and fall faster and faster until somewhere down here it thumps into the ground. So we have a max height event here, and then we have the hitting the ground event over here. And I think they're going to ask us about both of them. Yeah, the first one they ask about is the maximum height, which occurs at the top, red dot. Now, if you're at maximum height, it means you've stopped rising, and so your velocity has reached zero. I said here this velocity would go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And at some point you're going to run out of velocity. At that point, you're at zero velocity. That's when you're at max height. You're not going to rise any further, and in fact, an instant later, your velocity goes negative and you begin to fall. So this is the defining thing about your maximum height, is it's when you run out of upward velocity. And they want to know how high is that velocity. So we're trying to find how much of a distance is there between where we started and when we get to there. We want to know that d. So we have initial velocity, we have acceleration, we have final velocity, and a formula you might consider using that actually wouldn't work that great would be distance equals VIT plus 1/2 AT squared. We want the distance, we have the initial velocity, we have the acceleration, so that's sounding good, but we don't know how much time it takes to get to the top. Although, you know what, we could find that. That wouldn't be so bad. Maybe I'll do it two ways. You could do this, and then to get that time, you would use VF equals VI plus AT. Now, remember, that formula is not exactly on our data sheet. It's given in a different form and it takes a little manipulation, but I think I've mentioned before that this formula is a real winner and that it's worth knowing. If you have this, you could find that time to get to the maximum height. Our final velocity would be 0. That's the one you end up at. We started at plus 10. Acceleration's -981, and from that we get a time. Let's actually do that. We'll get VF is 0 equals 10 plus acceleration's -981 times t. Take the 10 to the other side, -10 equals -9.81 t, and divide both sides by 981. And I didn't have my calculator ready, so give me a moment. 10 divided by 981, just over a second, 1.02 seconds. Now that we know that, we can go to this distance formula and see how much we've risen. That distance would be VI, which is 10t plus 1/2 A is -981, and then we have 1.02 for the time, and don't forget to square it. So if we do all that, 1.02 squared, enter that wrong, try again, times 1. Okay, plus 10 times 1.02 is 10.2. I get 5.3 0 or 5.10. 5.10 meters. Now, important thing, that's 5.10 meters from here, and they said this point was 14 meters above the ground. So the real max height would be 14 plus 5.10. Plus 14 gives us 19.10 meters. So that's the highest that this object ever gets. The other way you could have done this, I won't do it to save a little bit of time, but another option we could have had is Vf squared equals Vi squared plus 2AD. Final velocity is 0, initial is 10, acceleration is minus 9.81, and we could have solved that for the distance, and that again would have, it should give us 5.10 meters if all goes well. So, nice to have options. 19.10 meters is that max height. I'll put that in the diagram, and then we'll see what else they want. Okay, now that I have that distance, I'll lose this because we need the space. If your camera is designed to withstand a speed of 21 meters per second when it hits the ground, will the camera be damaged beyond repair? Okay, they're talking about a different time now. Now we're talking about what happens when the camera goes crunch down here. And they're asking how fast is it going? V final here equals, we don't know how much. Now, if you throw an object up 10 meters per second from ground level, then when it comes back down to ground level, it'll be going minus 10. There's always symmetry there. But that doesn't work if you throw something off a ledge or drop something from an aircraft and it falls to lower than its original height. In that case, this velocity will be faster than minus 10. And to find it, let's see, we need something that involves Vf. And again, our options are Vf equals Vi plus At. This is not great because we don't know what time it is when we hit the ground, and while we could find that, I think there's a better way. And the better way would be this. Great formula, comes in useful all the time. Vf is the final velocity. Vi will be our positive 10. Acceleration is minus 981. The distance here is how far is it from the beginning point to our final point? And the answer there is minus 14 meters. We start at 14 meters above the ground. We end up right on the ground, so D is minus 14. Important to get that sign right, obviously, or you'll get wonky results from doing this. So we have Vf squared, I don't know it, equals Vi squared plus 2. Acceleration's minus 9.81, and the distance is minus 14. So if we do that, Vf squared is 10 squared is 100. Even I can do that one. 2 times 9.81 times 14. I know the negatives will cancel out, so I'm not worrying about them. We get 100 plus 274.68. Add those together, and you get 374.68. And square root that, you get 19 point. Okay. Technically, when you solve this, you get Vf equals, and it could be positive or negative 19.3, or I guess it rounds to 19.4. 19.4 meters per second. Now, technically, both of those answers are valid. The reason for that is, as far as the math is concerned, this object has been following this path forever, and that means it's been following that path back here too. The math is saying back here, if you were at ground level, the object would have been going 19.4 meters per second up. Now, that doesn't actually make sense because the camera was in our hand back here, but the formula doesn't know that. The formula thinks that this acceleration and this distance have been true forever, and so it's finding every place that they could have happened, including in the past. So in a weird sort of way, that positive 19.4 does work, assuming that the object has always been flying in this same trajectory. Now, that's not the case, so we're going to ignore that one, but That answer is not complete nonsense. There is an interpretation where that number does make some sense. However, the negative one makes even more sense. That's the one we were after, the one where we're over here. So one thing about this formula with the VF squared, it does give you positive and negative solutions, and sometimes you have to consider a moment to make sure you get the correct sign. In this case, the object's going downward as it hits the ground. Its velocity should come out negative. Negative 19.4 meters per second. Now, they said this camera can tolerate an impact of up to 21 meters per second, so this actually should be okay. And last thing, determine the time required for the camera to hit the ground. We only have a couple of time formulae that would work. We have the VIT plus 1 half AT squared, which is a real nuisance to solve for time, but there's a much better option. And the much better option is this thing I keep hyping to you. VF equals VI plus AT. VF is minus 19.4 meters per second. Initial velocity is positive 10. I partially erased it here, but that's what we started out with. Acceleration is minus 9.81. Don't forget that negative or terrible things will happen. And we can solve that for t. So subtract 10 from each side of this. We get minus 29.4 equals minus 9.81 t. And then 29.4 divided by 981 gives me, it's pretty much exactly 3 seconds. Yeah, it actually does round to 3.00 seconds. So, not too bad. When you have things moving upward and then downward, it gets very important to be good about your signs. And other than that, it's just about selecting the proper formula. This one is a champ. This is another champ. And in case this is the first video you've watched, the data book that we have, or the data sheet that we have, gives this as acceleration equals VF minus VI divided by t, or something pretty close to that. So this form's sort of okay. This is a modified version of that same formula. You multiply both sides by t and then you move the VI over. You get this, which is lovely to work with. I highly recommend it. I'd say memorize this or write it down on your sheet. It's going to come up over and over. I am a big fan, and I hope that you're a big fan too by the end of a few of these videos. Okay, enough about that. Let's crush another one. Sorry, I'm using a new recording system, and it doesn't have a slick way to clear the whole screen, at least. Or if it does, I'm not remembering it right this moment. So you get to watch me erase. All right, and hard-throwing baseball pitchers can deliver pitches at 160 kilometers an hour. If a pitcher throws a ball, if they could throw straight up, how high would the baseball travel to reach its maximum height? So, if something starts here and has an initial velocity of 160 kilometers per hour, that's pretty good. That would go up, and it would go 150, 140, 130, 120, 110, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. Right up here at the top, there will be a point where the velocity, the vertical velocity, hits 0. That's when the ball stops rising. And then it'll go minus 10, minus 20, minus 30, and fall back down. And after a moment, it will hit the ground. And because we start and end at ground level, it will hit the ground at minus 160 kilometers per hour. Right? So that's something that we know is always going to happen when we throw something and it starts and ends at the same level. I don't know if it's going to be critical in this problem, but it's a nice point to know. And they want to know, how far is it to this maximum height? In other words, what is the maximum height? What distance do we cover doing all this? Well, in the previous problem, I did something where I found the time to get from VI to VF, and then I used that time to figure out the distance, but there is a slicker way, and let's use the slick way this time. That would be VF squared equals VI squared plus 2AD. If this is our initial where the throw starts and we're calling this the final when we get to the top, then at the final velocity is 0. Initial velocity is, and now we have to hit pause for a second. This velocity in kilometers per hour is no good, or if we do use this, we would have to give our acceleration in kilometers per hour squared and our distance in kilometers, which would be really bizarre units. So let's get that fixed. Let's talk about unit conversion. If you have 160 kilometers and you can travel that in 1 hour, the units we want are meters per second. So we have to convert this kilometers into meters, and we have to turn this time into seconds. And there are a few ways to do this, and the simplest one is what they call dimensional analysis or unit conversion. And it goes something like this. We're going to say, I hope you know that there are 1,000 meters in 1 kilometer. You can write 1,000 meters is the same as 1 kilometer. And once you've done that, the kilometers cancel out. The 1,000 is still there, and we're going to have to use that. But now our unit for distance is meters. Also, if you happen to know that there's 60 minutes in an hour, you can say 1 hour contains 60 minutes, and then the hours cancel out. Why did I put it this way and not 60 on top? Because I need these hours and these hours to cancel, meaning one of them has to be on the denominator and one of them in the numerator. If you put both of them in the denominator, nothing cancels and you get a terrible mess. So you're always setting up units so that units that are currently there will cancel against the units you've just added. Now, one more step here. Minutes is not what I want either. I need seconds. So there's another line where you say 1 minute is the same as 60 seconds. Minutes cancel. And to get a number out of this, what you do is 160 times 1,000 times 1 times 1, which obviously we're not going to do. It won't change anything. Divided by 1, divided by 1, those don't matter either. Divided by 60 and divided by 60. So on the calculator, the ones that actually matter are 160 times 1,000 divided by 60 and divided by 60 again. And when the dust settles from all that, we find out that 160 kilometers per hour is 44.4 meters per second. So when they said their initial velocity was 160, 44.4 meters per second is the number we really want. And generally, if I'm doing a problem, I will skim through for bad units like this and convert them immediately, because you don't want to use this at all. There's almost no case where that's going to be useful to you, so get it out of there. Our initial velocity is 44.4 squared plus 2. The acceleration is minus 9.81, and we don't know d, but we're going to find it. Okay, you know what? I should carry an extra at least one more decimal point here just to make sure that nothing strange happens. We don't get any round off errors. 44.44 squared is 1974.91. Take that to the other side. We get minus 1974.91 equals minus 19.62d. And then we divide both sides by 19.62. Negative. And I find that the distance is almost exactly 100 meters. It's 100. Well, it's 100.7 meters, but really we only have 3 significant digits to work with, so we'd have to say it's exactly 100 meters. Fair enough. Again, we could have done this by finding time using, I'll do this really fast, An alternative way to do this would be Vf equals Vi plus At. Final velocity is 0, initial is 44.4, acceleration is minus 981. That would give you the time. And then you could use distance equals VIT plus 1 half AT squared to get the distance. But I think this is more work, and this formula is terrific for problems like this, so might as well make friends with that one, I would say. That's a good formula that's going to come up a lot.